we're going to talk about partial derivatives, and we're going to build up to three-dimensional optimization. Now, we can, of course, talk about going beyond three-dimensional optimization, and we'll talk about that a little bit right now, and we'll see a little bit of those tools towards the end of the semester. But let's take a step back and ask why we want to do any of this at all, right? So why does three-dimensional optimization matter? Well, as far as I know, the first case, and this is my biased experience, is to get an econ PhD, right? Or really any other technical PhD. Being able to get through these models is just a part of that process. To just survive your coursework, you've got to be able to handle this, higher dimensional math. Because it is a mathematical venture that you're undertaking if you're getting a PhD in a wide range of topics, right, besides the humanities or history. More likely, and particularly likely for people in this class, is because after a few years of working as an analyst, maybe decide, you know what, I'd like to make more money. I'm going to go take some data science classes and learn how to move up from data analyst to data scientist. Or, you want to learn some econometrics or, some formal statistics, just kind of under this larger umbrella of building some technical tools that allow you to work with data to extract useful information. In a case where you're trying to understand why and how these tools work, you are going to need partial derivatives and some of this multidimensional calculus. Now, it all sounds intimidating, but actually it turns out we've got sort of a nice simplification we can make when we're going down this realm. What we're trying to do, right? So in the realm of, say, econometrics, you build a model that predicts some value. Right, we're going to call that y hat. Y hat is our prediction. Let's not use that color. Let's use blue. Y hat, this is our prediction, and y is the true value, right? So we're trying to say, predict, is some customer likely to default on their loan? Or if we put advertising in front of this person, are they likely to buy our product, right? So y is some observed truth, and y hat is what your model predicts, and of course you're trying to get a model that does a better job. So how do you do that? Well, fundamentally you want to close this gap between these two variables, but in practice you square that difference. You're minimizing squared errors. This is happening all over the place. For plenty of good reasons, but we don't even need to get into that. It turns out this is pretty easy. We've got problems we want to solve. We want the derivative of this error term. Well, that derivative, we just pull down that 2, right? And we got 2 times the difference. That's pretty easy, right? That's sort of the very generic derivative. But it turns out when we learn the tools necessary to go deeper, to go into more dimensions than just a function of x and y, but also of z or ABC, whatever, we start learning some linear algebra. Or sometimes we call it matrix algebra, but it's the same thing. Cool thing with linear algebra is the difference between 40 dimensions and 40 dimensions is trivial, right? It hardly matters. It is the easiest thing in the world, at least for you as the data scientist or economist. Adding extra dimensions with linear algebra is pretty easy, right? So our model in linear algebra might look something like this. Y hat is beta times x, where x is some n-dimensional matrix. So x is our data, and we've got 50 things that we know about some object that we are using for our model to predict their outcome. So that means we've got this beta parameter that we're trying to change, and this is going to be a 50-dimensional thing also, right? So in the case of least squares, we're going to have these slope coefficients for these different dimensions of our data, and that's going to give us some prediction, right? So we want to improve the quality of our model, we want to minimize those squared errors. So let's do a slightly different version. We're going to say, let's minimize 1/2 of the squared errors. Why do we do that? Because, well, now when we take that derivative, the 2 cancels with the 1/2, and we're left with y hat again, minus y. And ideally, we want to set this equal to 0 and solve for beta, right? So in this case, we're taking partial derivatives with respect to beta. We don't get to choose x. We don't get to choose y. Y is just the ground truth, and x is our observed data. But what we can do is we can update in the right direction. So if we calculate this value, right, and this value is really easy to calculate. This is just the result of our model minus what is actually the truth. And if we have less than 0, we increase beta. If we have greater than 0, we decrease beta, and that's going to be moving us in the right direction. How do I know it's as simple as this? Well, it's because I know the sign of the second derivative. When we take the second derivative, we're taking the derivative of this. That's just going to be beta. That's greater than 0, which means that we are minimizing. We're looking at something shaped like that. So given that, this is all we have to do. This is the application of linear algebra, right, which is kind of a scary way to add dimensions. But this all boils down to, well, this is what you're likely to see, right? Why do we care about partial derivatives? Because we've got this application, and to understand what's going on, we're just going to dig into the tools underlying that. We're going to dig into the nuts and bolts and actually see it in action. I've kind of given away the punchline here, but let's just take a look at partial derivatives, and then we'll stop and we'll look at the overall procedure. So if we want to take a derivative with respect to x, right, we've got 5x to the n. F prime is 5 times n times x to the n minus 1. Power function rule, piece of cake, no problem. If we do that for some variable a, right, so let's say a is just some constant. Let's say a equals 5. Well, our derivative of a times x to the n is a times n times x to the n minus 1. Same as up here. No problem. Now let's change a. We could, it could be b, could be any letter. So let's make it y. And again, we do the same thing. We get y times n times x to the n minus 1. The basic derivative rules are going to apply to a partial derivative. Now the change going on right here is if instead of y being actually a constant, y is some variable in our model, right? And that might be a statistical model where we're trying to predict some specific outcome. If y is a real variable that isn't just a constant, this is no longer the derivative with respect to x, right? So over here, let me change colors. This is df dx. When y is a variable, it's this slightly different d. It's partial f, partial x. So to actually take a partial derivative, easiest thing in the world once you know how to take a derivative. Why do we care about this? First, because it lets us add dimensions, right? And that allows us more modeling power. That allows us to describe more elaborate, more realistic situations. Why would we ever want to do that? Well, maybe we go on to get a PhD and we have to deal with abstract mathematical arguments. And that's fine, right? That's a life choice that you might make. But it's a pretty rare decision to go get a technical PhD. More likely is you want to learn statistical tools to use in business that's going to help you to make more money. You want to go from being an analyst, or even you just want to be a senior analyst and you want to be better at that job, you need to understand how your models work, right? So here I showed just one simple model, but underlying this whole thing is going to be this updating procedure where you're applying these partial derivatives, which you're calculating down here, in order to improve the quality of your model. What does this all boil down to? Well, it boils down to it's helpful to know how your tools work so that you can be better at using them. All right, let's stop here. I said I was going to do the whole thing in under 15 minutes, but I'd rather do two 10-minute chunks. So up next, we're going to talk about our procedure for optimizing a function using partial derivatives in 3 dimensions.